Hello, welcome to the first episode in this series where I'll show you the basic tools you need to start solving problems in quantum mechanics. The idea for this series is that anyone with algebra can actually do some quantum mechanics. And I'll go over a few of the background ideas we need from classical physics in this intro video, and then we should be good to go. By the way, my name's Dylan. I have a degree in Physics and Astrophysics, and I make videos for this channel, Propulsion. I generally talk about science, but I also solve puzzles and build stuff. Now, I've generally seen quantum mechanics taught in two different ways. Either very conceptually, in a way that the general public can easily walk up to and understand, or using very high mathematics in a physics setting, and it's often very abstract in a way that sometimes even people studying physics don't understand. But the goal with this series is to meet those two in the middle. So we are going to look at equations. We're going to use them as our tools. I am going to try and include as many examples as I can, mostly after this intro video. That said, this is not going to supplant an actual course in physics. Most of what we talk about are things that my professors would call baby quantum, because we are going to avoid calculus as much as we can, and we're really not going to look too hard at things like the Schrödinger equation. But it's surprising how much you can still figure out using the basics. And as I mentioned, this video is going to focus on the background information we need before we get to the quantum physics, but by part 5, we'll have all the tools we need to analytically derive the Bohr radius, which is the approximate radius of a ground state hydrogen atom. That's pretty cool, and if you've seen all the videos until that point, it should make pretty good sense. So make sure to subscribe if you don't want to miss a video, and if this series does get good support, I can keep going too. We can make a second season and actually maybe explore more complex ideas as well. But without further ado, let's jump into the physics. To start off, let's look at some of the units we'll be using. So for mass, we'll be using units of kilograms. For length, we'll be using units of meters. For time, we'll be using units of seconds. And then all those are probably pretty well known. Then we get to charge. We'll be using units of coulombs, C for coulombs. Now every other unit we use can actually be pulled out of these guys here. So I guess for one simple example, we can use velocity, and velocity is equal to change in position over change in time. And so the units for that will be position, or length, that'll be meters, over time, seconds. So that is meters per second. Makes sense. That'll be especially useful for something like what we're doing here, which will involve a lot of the speed of light, c. So c is about 3 times 10 to the 8 meters per second. That is about the speed of light. Now let's talk about some of the other things we see here. For example, this times 10 to the 8. Now that is a power of 10 we're multiplying by. Also, in other words, you can think of that as the number of zeros after our decimal point. So you could also, if you wanted, write that as 300 kilometer, or times 10 to the 5 kilometers per second. So we're just taking 3 of those decimals we've moved, 3 of those zeros, and then saying that's kilometers. So can kind of change out those powers that you see for an additional part of the unit. And so that'd be kilometers. If you wanted to go the other way, you could have millimeters, or then below that you'd have micrometers, because we'll be going down to pretty small scales for quantum here. You can have nanometers as well. So yeah, kind of start out with meters. You can go up to kilometers, down to millimeters, and so on and so forth, each direction. And again, for our sake, go down to micrometers and down to nanometers. And then we're not going to worry about the big stuff. But another thing you see here is, why do we have 2 zeros after our decimal? Well, that is to signify the number of significant figures there. So for this, we're saying that there are 1, 2, 3 significant figures. If we were to do a calculation after that, then we would actually want to make sure our answer also had 3 significant figures, or the number of significant figures as the least precise measurement we had. So, if we were to multiply this by maybe something that we had only 2 significant figures, then you would want your answer to have 2 significant figures. Okay, that's some basic stuff. We've got units, we've got combining units, we've got powers of 10, magnitudes, and also we have significant figures. That is the first thing I wanted to talk about. Next, let's get to a few equations. All right, let's start off fairly simple with the equation for momentum. So for momentum, we're going to use the letter P, and it is equal to mass times velocity. Makes sense, right? So if something's really massive, it's going to have more momentum. If something's moving really fast, it's going to have more momentum. So that's great. And we can actually then look at something like force. It's a good another one. So let's look at Newton's second law here. So for force, we have F equals ma. You'll notice those two are kind of similar, right? But here we had velocity, and here we have acceleration. And so for velocity, if you remember the units, it was meters per second. Well, acceleration is actually, write it over here, acceleration is change in velocity over change in time. So our units for that would actually be meters per second squared, because you're having another change in time. And so for force, you can also write that, because we have velocity right there, right? You can write Newton's second law as change in momentum, and we're not going to worry about calculus, so I'm doing lots of these delta signs that mean change over change in time. So our next equation, and just very important concept here, is total energy. And if we're just talking about classical situation, we've been doing up here, then our total energy is equal to the kinetic energy, energy of motion, plus potential energy right there. So we're just adding up the kinetic and potential energy, and that is equal to the total energy. But we also have an equation for kinetic energy. And that is E equals 1/2 mass times velocity squared. And there's a little in our way there, but yeah, that is our equation for kinetic energy. And you'll notice we have this bit here, that mv squared, that looks a little similar to momentum. There's actually a useful way you can rewrite that as momentum squared over 2m, right? So you still have that 1/2 there. We square the whole momentum. It's okay to leave the velocity, but then we have to take one mass out because we were squaring it. So that is another way you can write kinetic energy. That will be extremely useful later on. And one last equation I would like to write down, though I likely don't need to, is rest mass energy. So rest mass energy. And for that, of course, E, it's not a very good E. E equals mc squared, of course, very classic. Now what I'd like to do is tie a few of these up into an example, just so we can kind of sit with the ideas, and then we'll call it good for this video. So I think there's a pretty nice, succinct way to wrap up those first couple of equations with an example to show something that Galileo noticed a little over 400 years ago, which is the height of an object, or the change in height of an object dropped here on Earth, is proportional to the time elapsed squared. So in other words, as you drop something, it actually accelerates down towards the Earth. It'll go faster and faster. And we'll take a more complicated route to get there than Galileo did, but it'll use those equations that we talked about. And so we can think of that situation as some initial energy, some initial total energy, and then some final total energy as it right before it hits the ground. So we're taking potential energy, converting it to kinetic energy. So let's think about that as an initial energy state, and that will be equal to the final energy state. Now I mentioned this guy is all just wrapped up in potential energy, and this guy's all wrapped up in kinetic energy. So let's go ahead and rewrite those guys. We'll have the potential energy, and I didn't mention this at first, but this is gravitational potential energy. It's the mass times gravitational acceleration. So we'll actually use that in a minute with Newton's law. This is acceleration from gravity, and that is we're using it as the total change in height. Or in other words, just height above the ground. So that's our potential energy. That will be equal to the kinetic energy, which we looked at, 1/2 mv squared. Now we did talk about another way to write that using momentum, and that was p squared over 2m. And that's what we're going to use here to eventually bring time in without any calculus. So what we can do is get this in terms of momentum, and that will turn out to be, let's just do p squared and then multiply that guy over there. So that will be 2m squared gh. Take the square root of this guy, so that will disappear. That square on the m, and then we're left with p is equal to m times the square root of 2 2gh. Now, let's go ahead and bring this over to Newton's second law, which again we had F equals ma, but in this case, A is gravitational acceleration, right? So let's go ahead and write mg, acceleration, gravitational acceleration, that is equal to change momentum over change in time. Now, something important here is this is only going to work because we're saying that the force is constant. In other words, the mass is constant, the acceleration is constant. Otherwise, this wouldn't work. Then we'd need calculus. But for this example, that is totally fine. And so what we can then write is pull this guy into there. So we're doing change in momentum, which is just that, just constant. That will be m 2gh. And then let's just keep that as delta t for just time elapsed. Now then, actually, you know what? I changed my mind. Let's make that t. Time from when we drop our object to when it hits the ground. All right, so now we have that. It's equal to that guy there. So let's use those two. You'll notice the masses actually cancel. Awesome. Another thing Galileo noticed, as you drop something, doesn't actually depend on the mass. More massive doesn't necessarily mean it'll hit the ground first, so that's great. Masses cancel. Now we want to find height, right? And show that it's proportional to the time elapsed squared. So let's go ahead and multiply time over. So now we have gt square root 2gh, and then go ahead and square that guy. So now we have g squared t squared 2gh. Now we can divide one of these g's over. So then that'll get rid of the square. And now we're almost there. We just divide the 2 over. We get height is equal to, get 1/2 g t squared. Awesome. And as you'll notice, we have height on one side, t squared on the other side, and this in fact is true. And we used a whole bunch of equations to show it, which there are simpler ways to do it, but I thought this would be nice just to kind of pile everything in. All right, that is the end of part 1. Congratulations, and let me know if you have any questions. Don't forget to subscribe so you don't miss part 2. I'll see you there, and thanks for watching.